This is our fifth and final lab. I decided to track the motion of an object with velocity in 2 dimensions. I then also created a model in VPython to predict the trajectory that the object should have. I found that if I with a drag constant p, I can make the motion in the y direction line up pretty closely. However, in this course, when we have an object traveling in 2 dimensions, we do not take horizontal acceleration into consideration. I tested this practice and found that in my tracker, it's not entirely accurate. I started by setting the origin at the place where I released the ball, keeping the positive x-axis up and the positive x direction as to the right. Here's my video. I then took the video in this tracker and put it into an Excel file. I then modified the code from Lab 2 so that I could put in 2 dimensions. I also used guess and check on my b value to find the correct value to make the y components line up. When I run this code with the appropriate drag constant, here's what I get. Here are the principles and equations that I used, including the correct drag constant. Here's my model compared to the actual data without drag taken into effect. As you can see, the models are close, but not perfect. When I run that with drag coefficient, the values in the y direction line up much closer. In the middle areas, it still does not line up perfectly, but I'll discuss that later. Now, I did not make graphs for the x components. This is because in our class, we've been assuming that x velocities are constant in problems where gravity is the only force acting. Of course, in this lab, there are other forces, such as drag. As you can see in the model, the velocity stays constant at 3.16 meters per second. However, in tracker, the initial velocity is 3.16, but the final velocity is 2.81 meters per second. This means that there must be some force acting on this object in the x direction. Now, what does this mean? This means that we cannot just assume that in the real world, a projectile has no change in momentum in the x direction. This video shows that there must be something acting on this object in the x direction. This video is only 0.8 seconds long, and the ball decelerates by over 0.3 of a meter per second. That's a significant change in velocity. The other question that I looked at was about conservation of energy. I looked at the magnitude of the velocities at equal heights on either side of the vertex of the curve and compared their kinetic energies. Since they're at the same height, they should be equivalent according to conservation of energy, but they are not. This is obvious since I did not look at the loss of energy due to drag or other non-conservative forces. Finally, I looked at possible sources of error. First of all, if you watch my video closely, there's some movement in the camera. This certainly would cause problems in tracking the object. Also, the lighting was not great, so I was guessing on the points of mass while I was tracking it. Also, I only used guess and check to find my b value, which is not the most accurate way. More than that, I didn't explore the x direction with drag, which explains why my code didn't model the object losing velocity in the x direction. What I found in this lab is that velocity is indeed not constant in the x direction when gravity is acting on it. We must take drag into effect to accurately model the ball's velocity. This compounds many errors in other topics. For instance, my energies are not equal for equal heights because I did not find the correct velocity. This means that since my original code was wrong, many other aspects of the systems would be wrong. Back on energy for a second. The reason that we can say that the velocity should be equal in a theoretical case is because the work that gravity does on the object cancels out. When it goes up to the vertex, work is equal to negative Fd, but on the way back down, it's equal to Fd. Therefore, they cancel out, and the change in energy should be zero. Of course, this isn't true in practice, though, because there's loss in energy to drag and other non-conservative forces.